So now we're going to do number 7 from this sheet. Number 7 right there. Of course, you're going to have 1 through 8 for homework. Somebody asked me a while ago, if I do number 2 and number 7 in the videos, then do you still have to do it for homework? Yes, you do, because that's basically showing that you took notes on what we did here, okay? All right, so number 7, they give us acceleration. So we have to work all the way up the ladder, right? So we go up to velocity, we're going to go up to position, so we're going to have to integrate twice. And we're going to have to supply information at each step. All right, we have to supply information at each step. That's why if you start with acceleration and you want to get a position function, you have to have 2 pieces of information supplied. Every time you step up that chain, you've got to have a piece of information that was lost when a derivative was done. All right, so that's why 2 pieces of information if we're starting with acceleration. All right, but those 2 pieces of information could be for anywhere. It could be v of 0 and s of 0. It could be v of 5 and s of 3. So all we need to know is the velocity and the position at any 2 times, and then we can determine the position and velocity functions for all time. You could also do this with just 2 different position pieces of information. That happens in number 8. And by the way you're going to have to solve number 8 is using a system of equations, but I'm going to let you figure that out. If you don't, then we'll do it in class. But you got to at least make a good faith effort to try and figure it out on your own, because that's what we're about. Figure things out on your own. All right, so we're going to say, first of all, the velocity is the indefinite integral from e to the 2t dt. So this is again one of those with an inside function that is linear. So let's think about how we would do that antiderivative if I thought about what I said last time about it, which is that I'll do the antiderivative of the outside function, which is, the antiderivative of e to the x is e to the x. Keep the inside function the same, and then instead of multiplying by g prime like I would do in a chain rule, I'll multiply by 1 over g prime. All right, so that's like 1 over g prime. So that's like a mini version of the full integration by substitution that we're going to do later. All right, so let's just check that works. If I do the derivative with respect to t of 1/2 e to the 2t, what would it be? Well, I would keep the 1/2. I would do derivative of e to the 2t, chain rule, derivative of the outside, keep the inside the same, multiply times the derivative of the inside function, which is 2. The 1/2 and the 2 cancel out, and I get e to the 2t. So in fact, this 1/2 e to the 2t that I got by using 1 over g prime is in fact an antiderivative of e to the 2t. So now, remember that this is an indefinite integral, so I'm not going to put brackets. I don't have limits of integration. We're actually going to talk more about indefinite integrals next time. But for now, we can just sort of see how they work. So I'm going to use this, 1/2 e to the 2t. So that's 1/2 e to the 2t. But because an antiderivative, all antiderivatives, are, because the derivative is invariant under vertical transformations, that means the antiderivative could add in any vertical transformation. That's another way to see that, So it's like, here's e to the 2t. Here's a graph of e to the 2t, right? And then, so the possible antiderivatives, which are 1/2 e to the 2t, so this is going to be slightly shorter, okay? But they could have any vertical transformation, right? These are the e to the 1/2 e to the 2t plus c. The c's are just moving it up and down, where this is our original e to the 2t. So that's how you can think about what that plus c does graphically. It says any vertical transformation would give me the same derivative. So the antiderivative has to include any possible vertical transformation, which we do by putting the plus c. So that's another important way to think about that. All right, so now what we're going to do is we're going to use our given information to find out what the c is. So we know v of 0 is 1.5. From this, we know v of 0 is equal to 1/2 e to the 2 times 0 plus c. And from this, we know that equals 1.5, right? So v of 0 equals 1.5, v of 0 equals 1.5 equals this. And then we can use that to solve for c. 2 to the 0, of course, 2 times 0 is 0, e to the 0 is 1, so I really have 1/2 plus c equals 1.5, so c equals 1. So now what I'm going to do is I'm going to go back to my v of t, and I'm going to put in the c equals 1. v of t now equals 1/2 e to the 2t plus 1. That's combining my original expression for v of t that I had here with my new knowledge that c equals 1. All right, so now I've got an equation for v of t. Now I can get an equation for the position function, because s of t is the integral of v of t. Should I write that first? No, I'm not going to. My v of t is 1/2 e to the 2t plus 1 dt. All right, always dt with your integral, or dx if you're doing with respect to x, this is with respect to t. All right, so now I'm going to do this antiderivative. All right, so it's not too hard to realize then that if I did the antiderivative of e to the 2t is 1/2 e to the 2t, but I have a 1/2 already multiplied by that, so that means I'm going to have 1/4 e to the 2t. And what's the antiderivative of 1? What's the antiderivative of 1? What is it? That's right, it's t. All right, and then I'm going to put plus c. Right, so if the c turned out to be 5, then I'd have 5t right here, right? So that's how we sort of reconstruct the lost information that occurred in this process. We reconstruct it by using the given information, and now I know that that was 1t and not 7t or something like that. All right, so, but now I need to find out what this c is. By the way, these two c's are different. So, I mean, it'd be nice, I could call them c1 and c2, but most people don't do that. They'll just say, you know, c is like this floating constant. All right, so now what? Oh yeah, now we know s of 0 is 7.3, so we're going to put that in. We're going to say s of 0, which equals 1/4 e to the 2 times 0 plus 0 plus c. I mean, this could have been s of 5, and then we put 5s in there, all right? And then that equals what it says s of 0, which is 7.3. So what we're using now is we're using the s of 0 equals 7.3. We're putting that here. Yeah. And then we can use this part to solve for c. So 1/4 times e to the 2 times 0 is 1/4. So I have 1/4 plus c equals 7.3. 1/4 is 0.25, so this is 7.05. And then I just put that into my s of t that I had up here. So s of t is equal to 1/4 e to the 2t plus t plus 7.05. That's what I get by combining my s of t that I had with my c that I just calculated. All right, and now I have fully answered the question because I have a of t, which was given. I have v of t right there, and I have s of t right there. So what this has allowed me to do is take an equation that just gave acceleration and two particular points of information and construct from that the velocity function that tells me the velocity at any time t and the position that tells me the position at any time t, right? At first, I knew the acceleration equation and the velocity at one time, time 0, the position at one time, time 0. These don't even have to be the same time. That was just to simplify it. All right, and from that information, I can construct the velocity at any time, the position at any time. That's what we're doing in this exercise. We're creating an equation for s of t, v of t, and a of t, and I gave you just different things to work from every time. So you can work back and forth. All this is about is saying that once I understand the total relationship between position, velocity, and acceleration, that I do derivatives going down and integrals going up, that when I'm going up, I need to supply information because when I was going down, I lost information. If I understand that, then you can have the information given at any point in this ladder and get the other two. If you have position, you can get velocity, acceleration. You already knew that. You have velocity, now you already could get acceleration, now you can also get position. And now, if you have acceleration, you can get position and velocity. So that is what we're talking about with advanced particle motion. That's everything that we wanted to say about the new take that we have, the new perspective, the new tools that we have for working with position, velocity, and acceleration. So the homework that is being assigned with this homework is, okay, the so there's this sheet. I wish I had my sheets together. I got to get my sheets together for this class. Distance and displacement. Distance and displacement. That's a worksheet. Advanced particle motion. All these, of course, are posted in the Google Classroom. You have to do all of them, all right? This is all the problems. Motion. Okay, we have to do all the problems. These are worksheets. And the other fun thing that you get to do is in your book, chapter 7, you're going to do page 386, number 1 through 4 all. So I could have written out 1, 2, 3, 4. It's a little bit of a toss-out as to which takes more symbols. And then 9, 11, 18, and 20, that's your random assortment for today. And there you go. Enjoy.